In last video, we went over solving a logarithmic equation, so let's now solve exponential. And these steps are almost the exact same. It says, if possible, use the property, if b to the u equals b to the v, then u equals v. So if these bases are the same, we'll cancel them out and set the exponents equal to each other, which was truly the exact same first step in my logarithmic equations. If I had log base b and log base b, you could cancel them out and set what was left equal to each other. So almost identical. Do the bases match? If we can't use this property, then we're going to follow these three steps. First, we're going to isolate the exponential. We will rewrite the exponential into a log, and then we're going to solve the equation, which is the exact same steps we had here. Both equations, whether it's exponential or log, isolate, rewrite, solve. Now with logs, we have a fourth step of checking for extraneous solutions. I put a little note down here. We don't need to check for extraneous solutions with exponentials. Why? Because the domain of all exponential functions is, and your symbol for all real numbers is a double line with an R. The domain for all exponential functions is all real numbers. So because there's not any kind of restriction on its domain, whatever my answer is my solution. There is no plugging it in and checking anything. So for example 2, part A says solve the exponential equation, express your solution in exact form. Exact form we put in last video, it meant no decimals. That's not really accurate. Exact form means no rounding. Now, a lot of times that comes with decimals. Okay, but if my decimal is 0.7 and it ends right there, then that's still exact form. It's when it's 0.7 repeating and I have to cut off some of those digits that I am not putting that in exact form anymore. So, example A, I'm going to use this property here. I can rewrite 16 with a base of 4. So that will be 4 to the 2x plus 1 equals 4 to what power gives me 16, and that's 2. So now we can cancel our base of 4 and set the exponents equal to each other. So 2x plus 1 equals 2. We're going to subtract our 1 and then divide by 2, and we get x equals 1/2. Okay, very similar on part B. We can still apply this property. I can now rewrite these both with a base of 2. Okay, how do I write 1/2 to the x power as a base of 2? That would be to the negative x. And we can write 16 as a base of 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. So now we have the same bases. We have negative x equals 4. So therefore, x equals negative 4. Okay, so we've already solved exponential equations like that. Now, once we get to part C here, I cannot write 10 as a base of 2. So that's where the second method's going to come into play. First, isolate your exponential. Well, it's only 2 to the x, so nothing's being added, subtracted, multiplied, or divided to it. So now we need to rewrite our exponential into an equivalent log. So if I go base to the other side of the equals, we get log base 2 of 10. And that equals what's in your exponent, which is x. Once I rewrite this one, I have already solved for the equation. It's already x equals. Now again, because I want this in exact form, this is my exact form right here. And so we are completely done. Now, if we wanted an approximation, we could put that in our calculator. We could say X is about, so alpha window number 5, my base, 2 and 10, that's about, we'll say 3.2. So if we need to round it, we can put it into our calculator using alpha window number 5, or use your change of base formula if you have an 83, and that would be log of 10, close your parentheses, divided by log of 2. But all of these digits over here, we are rounding and we are cutting out, so it's not exact when I write it as 3.32. This is my exact answer. Okay, on this one, same thing. I can't write 8 and 1.2 with the same base. So rewrite it. We're going base to the other side of the equal sign. So I have log base 8 of 1.2. And this equals my exponent. So again, instead of putting equals over here, I'm going to put my x equals over here. But this one actually equals negative x. So the exponential is already isolated. We have now rewrote it. Last step is to solve. Divide both sides by -1 or multiply both sides by -1. And we get x equals negative log base 8 of 1.2. This is my exact. I can put this in my calculator to get my decimal equivalent. Let's continue on to the next page. We have 4 more examples. These top 2 ones are as hard as our exponential equations are going to get. Okay, for my on-campusers, these are our test questions, and you can see these are the exact same. So what I want to do is we're going to solve E together, and then I want you to try pausing it and solving F on your own because they are exactly the same, just different numbers. So my first step is to isolate. I can't use this property here because they have different bases, right? So first I need to isolate. Well, I have this exponential already isolated and this one as well. So we are all ready to rewrite. When I rewrite this, it doesn't matter which way you want to start. I'm going to go, because this is an exponential with a base of 3. This is an exponential with a base of 4. So it really doesn't matter which way you go, but I'm going to go base of 3 to the other side of this equals. So log base 3 of 4 to the x equals what's left over, what's in this exponential right here. So 1 minus 2x. So now I need to solve for x, and I have x on both sides of my equation. So the first thing I'm going to do is this x in this exponent position does me no good. So I'm going to move this x to the front, and we have x log base 3 of 4 equals 1 minus 2x. So now that I have both x's on different sides, I need to get it to the same side. So I'm going to add my 2x over here. And now I have my x on the same side. Because both of these terms have an x, I can factor out that x. So that's going to leave me with log base 3 of 4 plus 2. This right here is a number. I can type this into my calculator and get a decimal equivalent. So this is x times a number. To get x by itself, I'm going to divide that over. So let's just go ahead and show it. We're dividing by log base 3 of 4 plus 2 and dividing this by log base 3 of 4 of 2. This cancels over here and I am left with x, and then I can't do anything here. So this is 1 over log base 3 of 4 plus 2. So there is my exact solution. Again, we can type this into our calculator to get a decimal equivalent. If I do alpha y equals, to get my fraction. We have 1 divided by alpha window for my log base of 3 of 4 plus 2. This is about, we'll call it 0.307. Okay, so we can get a decimal equivalent by typing that in, but if it wants exact, this is my exact with nothing rounded because I'm not cutting off all those decimals. Okay, so take a moment and try to solve F. Okay, I hope you had time to pause. So let's check your answer. Your final answer should have been 1 over log base 5 of 2 plus 3. So how did we get there? Well, the first thing I need to do is rewrite this. So we went base to the other side of the equals. So log base 5 of 2 to the x, and that equals the exponent, what's left over. Having an x in that exponent position doesn't do me any good. So next thing we did was move that out front. So now I have x log base 5 of 2. Now I have x on both sides of my equation, so I need to get x to the same side. So I'm going to add that over to get a plus 3x. Now both of these terms have an x in it, so pull it out. And we are left with x times log base 5 of 2 plus 3. This is a number, right? So we have x times this number equals 1. So divide it over, and we're left with this right here. So practice this. In my math lab, do similar questions, even if you get it right, to make sure you're getting good and familiar with this until it is easy. Going on here, G and H are problems that we're going to need next lesson in our last lesson of this class in lesson 8. So following our steps, first thing I need to do is isolate. This is already isolated. So let's rewrite. When I go base to the other side of our equal sign, I have a base of e. What is my log with a base of e? That's natural log. So we have natural log 13 equals what's left over, 10x minus 7. Then I'll solve for x. So we'll add that 7 over. And then divide by 10. So I'm going to get x equals the natural log of 13 plus 7 all over 10. And you can use your N over D button to get a decimal equivalent if it needs that or if it asks for that. H, we finally have to do all of our steps here. First step is to isolate the exponential. I don't have this isolated yet because this is 4 times my exponential. So the first thing I'm going to do here is divide that 4 over. So we're left with e to the 0.5x equals 8 divided by 4 is 2, 4 divided by 2 is 1. Now I have isolated this exponential, now we can rewrite it. So when I go base to the other side of the equals, a log with a base of e is natural log, so we'll have natural log 21 equals 0.5 x. And then to get x by itself, divide. So we get x equals the natural log of 21 over 0.5. Now you can try this answer in my math lab. I'm pretty sure it won't accept that as an answer. It doesn't like decimals in the denominator. And so dividing by a half is the same thing as multiplying by 2. So you might need to write that as x equals 2 natural log of 21. Okay, and when I say might, I'm like 90% confident that this is how it wants its answer. So let's say you have something different in that denominator, just kind of divide it. So here, this is the reason this is a 2. If you do 1, that's the same as 1 natural log of 21, right? So 1 divided by 0.5 it comes out to 2. So let's say it's dividing by 0.4. 1 divided by 0.4 gives you 2.5. So that might not be the best example, but you kind of get the gist. So just do 1 divided by whatever this is, and then that's the number that will go out in front.